Assalamualaikum warahmatullahi wabarakatuh and very good day. For chapter number 5, part number 4, we will discuss about stage performance for axial flow compressor. Okay, there are a few factors that affect the compressor state efficiency. So first we look at the total efficiency equation where mu Tt equal to delta W minimum divided by delta W actual and also equal to 1 minus delta P naught rotor, total pressure loss in rotor plus delta P naught stator, total pressure loss in stator divided by rho multiplied by H03 minus H01, stagnation enthalpy difference. Okay, so the schematic diagram shows the arrangement of guide vane rows, rotor rows, and also stator rows. And the red arrow shows the airflow direction. So we have condition number 1, condition number 2, and also condition number 3. So if you look at the total efficiency equation, so we have the term for delta W that represent the actual work done in the compressor. And the actual work done in terms of equation is equal to delta W equal to stagnation enthalpy difference H03 minus H01 equal to static enthalpy difference H3 minus H1 plus kinetic energy term for fluid half C3 square minus C1 square. Okay, so for the term of kinetic energy of fluid in the equation, if we consider normal state condition where C1 equal to C3, so this term will be 0. So the remaining term for actual work done is delta W equal to H03 minus H01 equal to H3 minus H1. So the term for H03 minus H01 in the total efficiency, if we consider normal state condition, we can replace with H3 minus H1. Instead, we use stagnation enthalpy difference. We can also use static enthalpy difference if we consider normal state condition. There are a few factors that affect the compressor state efficiency. First factor that affect the compressor state efficiency is the degree of reaction R, where the formula for R, we already learned that R equal to H2 minus H1 divided by H3 minus H1. So in the equation of R, we have the term for static enthalpy difference H3 minus H1. So when the value of H3 minus H1 change in the degree of reaction equation, the value of degree of reaction will be changed, and also the efficiency, total efficiency for the compressor also will be changed. So the second parameter that affect the compressor state efficiency is the stage loading, where the formula for stage loading equal to delta W divided by U square. So delta W here is the actual work done in the compressor. Okay, the third parameter is tangential force Y, the parameter that you have learned in previous chapters, where Y equal to rho, density of air, S spacing distance of the blade, Cx axial velocity divided by U blade speed multiplied by stagnation enthalpy difference H03 minus H01. Okay, the final factor that affect the compressor stage is the static pressure rise, delta P, which is equal to P3 minus P1. So the formula for static pressure rise is P3 minus P1 divided by rho equal to H3 minus H1. So all these factors will involve the enthalpy difference for the stage, whether the formula will involve H3 minus H1, static enthalpy difference, or H03 minus H01, stagnation enthalpy difference for the stage. So these four factors will affect the value of total efficiency for the compressor stage. So now we need to differentiate in terms of delta P definition and also delta P naught. So delta P refer to the pressure rise, the increase of pressure in the compressor, and delta P naught represent the total pressure loss in the compressor. So we need to differentiate between these two terms. Okay, so if you look at the schematic diagram, the schematic diagram shows the pressure profile throughout the compressor. So if we consider the ideal case of flow, so delta P roto S stand for the actual pressure rise in the rotor, ideal pressure rise in the rotor, and delta P stator S represent the ideal pressure rise in the stator. However, if we consider the losses or the friction or the irreversibility factor, so we will have, instead of we have delta P roto S, we will have delta P roto A, which is represent the pressure rise, the actual pressure rise in the rotor. And also we will have the actual pressure rise in the stator. So the difference between the ideal and also the actual pressure rise will give you the delta P loss, pressure difference in terms of pressure loss in the rotor and also pressure loss in the stator. Okay, so delta P loss in the stator, delta P loss in the rotor represent the pressure losses in the compressor, and this parameter will relate to the total pressure loss delta P naught. So now we have to differentiate between delta P naught and also delta P. So between static pressure rise and also the total pressure losses. So these are the difference between pressure rise and also total pressure losses. Okay, so the total pressure losses, if we look to the total efficiency equation, so we'll have two type of total pressure losses. First for the rotor and the second one for the stator. Delta P naught rotor and also delta P naught for the stator. Okay, stage pressure rise, delta P. So this parameter, stage pressure rise delta P, is important because the main function of a compressor is to raise the static pressure of air or gas. So we need to know what the pressure difference throughout the compressor stage. And the parameter that measure the difference is the stage pressure rise, delta P. Okay, so this is the schematic diagram for the blade rolls regimen. And if we consider the ideal compressor stage where no stagnation pressure losses, delta P not equal to 0, so we will have this kind of pressure profile where we have pressure rise in the rotor, delta P rotor, and also pressure rise in the stator, delta P stator. So if you combine both values, so we'll get delta P total pressure rise in the stage of the compressor. This total pressure rise, delta P total, represent the stage pressure rise, delta P. Okay, the second figure shows the velocity diagram at the inlet of the rotor, outlet of the rotor, and also outlet of the stator. So this stage pressure rise, delta P, actually depend on the flow geometry of the rotor, which means depend on the velocity diagram at the inlet and also outlet of the rotor, as shown in the figure. And the stage pressure rise, delta P, also depend on the speed of the rotor, the value of U. Okay, so across the rotor, we have to know that the relative stagnation pressure P0, P naught relative, is constant throughout the compression process, where we have equation number 1 where P02 relative equal to P01 relative, and the basic equation for P0 relative equal to static pressure plus half rho W square, represented by equation number 2. So manipulate equation number 2 and substitute into equation number 1. Thus static pressure rise in the rotor is equal to P2 minus P1 equal to half rho multiplied by bracket W1 square minus W2 square, represented by equation number 3. However, for the stator, across the stator, stagnation pressure P naught is constant, where P02 equal to P03, represented by equation number 4. And individual formula or basic formula for stagnation pressure is P naught equal to static pressure plus half rho C square, represented by equation number 5. Manipulate equation number 5 and substitute into equation number 4. The static pressure rise in the stator is equal to P3 minus P2 equal to half rho multiplied by bracket C2 square minus C3 square, represented by equation number 6. Add equation number 6 and also equation number 3, and also consider a normal stage condition C1 equal to C3. Implement velocity diagram and also trigonometry rules. The static pressure rise in the stage is equal to P3 minus P1 equal to rho U multiplied by bracket Wy1 minus Wy2, represented by equation number 7. Then use trigonometry and also velocity diagram rules. Thus, new expression of static pressure rise for a stage based on equation number 7 will be P3 minus P1 equal to rho U bracket Cy2 minus Cy1 equal to rho bracket H03 minus H01. Because we consider the normal stage condition, P3 minus P1 also equal to rho H3 minus H1, represented by equation number 8. Example 5.3. Question A. Figure 1 shows velocity diagram for an ideal compressor stage which has no stagnation pressure losses. The stage of the compressor is considered as a normal stage where C3 equal to C1 and alpha 3 equal to alpha 1 and has a pressure difference across the rotor and the stator rows as shown in equation number 1 and equation number 2 respectively. Prove that the pressure difference of the compressor stage is equal to equation number 3. Okay, question B. Based on figure number 1, air enters the compressor rotor at entry angle of 10 degree with absolute velocity of 50 meter per second. The rotor blade speed is 100 meter per second. The air deflects from the rotor with absolute velocity of 80 meter per second. For normal stage compressor, the axial velocity across the stage is constant. Determine enthalpy difference of the compressor. Okay, solution for example 5.3. First, the equation asks you to prove equation number 3. So equation given are as below in the equation. So first, the pressure difference across the rotor equation represented by equation number 1, P2 minus P1 equal to half rho multiplied by bracket W1 square minus W2 square. So the equation for pressure difference across the stator represented by equation number 2, P3 minus P2 equal to half rho multiplied by bracket C2 square minus C3 square. And the last is for the pressure difference across the stage represented by equation number 3, P3 minus P1 equal to rho U multiplied by bracket Cy2 minus Cy1 equal to rho bracket H3 minus H1. So now you need to prove that the pressure difference of the compressor stage is equal to equation number 3. First, consider a normal stage condition where C1 equal to C3 and add equation number 1 and also equation number 2. So we will have equation number 4 where P3 minus P1 multiplied by 2 divided by rho equal to bracket C2 square minus W2 square plus bracket W1 square minus C1 square. Rearrange equation number 4. So P3 minus P1 multiplied by 2 divided by rho equal to bracket C2 square minus W2 square minus C1 square minus W1 square, represented by equation number 5. Use cosine rules and also trigonometry rules for part of the equation number 5. So if we base on the general velocity triangle as shown in the slide, so we know that C square will be equal to U square plus W square minus 2U W cos theta. And from the figures, we know that the theta actually equal to pi divided by 2 minus beta. So we have new expression for C square, where C square equal to U square plus W square minus 2U W cos pi over 2 minus beta. Okay, by using trigonometry rules for cos, so we have cos pi over 2 minus beta also equal to cos pi over 2 multiplied by cos beta plus sin pi over 2 multiplied by sin beta. And cos pi over 2 minus beta also equal to sin beta. Okay, by using this what I call general equation for triangles law and also trigonometry law, so we can change part of the equation number 5. We can simplify the equation number 5. So the first term in equation number 5 is C1 square minus W1 square. If we implement the general equation that we have obtained before just now, so C1 square minus W1 square equal to U square minus 2UW1 cos pi over 2 pi over 2 minus beta 1 also equal to U square minus 2UW1 sin beta 1 equal to U square minus 2UWY1 represented by equation number 6. The second term for the equation number 5, C2 square minus W2 square, implement the general trigonometry equation and also triangle law equation. C2 square minus W2 square will be equal to U square minus 2UW2 cos pi over 2 minus beta 2 also equal to U square minus 2UW2 sin beta 2 equal to U square minus 2UWY2 represented by equation number 7. Substitute equation 6 and equation 7 into equation number 5, so we'll get more simplified equation where we have P3 minus P1 multiplied by 2 divided by rho equal to bracket U square minus 2UWY2 minus bracket U square minus 2UWY1 represented by equation number 8. Rearrange equation number 8, so we'll get equation number 9 where P3 minus P1 multiplied by 2 divided by rho equal to 2U multiplied by bracket WY1 minus WY2. So from this diagram, at the inlet of the rotor and also at the outlet of the rotor, so we know that if we refer to the this diagram at the inlet of the rotor, CY1 equal to U minus WY1, equation number 10. And based on the this diagram at the outlet of the rotor, CY2 equal to U minus WY2, equation number 11. Subtract equation number 10 and also equation number 11, so we'll get WY1 minus WY2 equal to CY2 minus CY1, equation 12. Substitute equation 12 into equation number 9, so we will get what I call the equation for pressure difference, where P3 minus P1 divided by rho equal to U multiplied by bracket CY2 minus CY1. So we already proved the equation for pressure difference equation for a stage that refer to equation number 3. Okay, for question B, in order to determine the enthalpy difference in the compressor, equation 3 given need to be reversed, where P3 minus P1 equal to rho U multiplied by CY2 minus CY1 equal to rho H3 minus H1, equation number 3. From equation number 3, enthalpy difference for the compressor equal to H3 minus H1 equal to U multiplied by CY2 minus CY1, equation 13. So from data given, alpha 1 equal to 10 degree, C1 equal to 50 meter per second, C2 equal to 80 meter per second, and U blade speed equal to 100 meter per second. And for constant axial velocity condition where Cx1 equal to Cx2 equal to Cx, and the value is still unknown, so we need to calculate by using the velocity diagram. And for normal state condition, C1 equal to C3, alpha 1 equal to alpha 3. So you have to draw velocity diagram at the rotor inlet to determine Cy1 value in equation 13. So you need to use your own scale. So first draw the vector for U, because we already know the direction of U and also the magnitude of U. Okay, so now by using geometry approach or graphical approach, use a ruler, compass and also protractor to determine the magnitude and also the angle of the vector. So because we already know the angle for alpha 1 and also the magnitude of C1, so we can simply draw the line for C1. Okay, from the C1 vector, we can determine the axial velocity value, where we just draw the upper limit and also the lower limit of the axial velocity based on the vector C1. So we get the value of Cx1, where the value is equal to 49 meter per second. And then complete. Okay, and also we can also determine the Cx value by using the trigonometry approach, where Cx1 equal to C1 cos alpha 1. So we already know the value of C1 and so alpha 1. Substitute into the equation. So we'll get Cx1 equal to 49.2 meter per second. Okay, so next we can determine the vector of W1. Just complete the velocity triangle at the inlet of the rotor. We just continue connect the initial point for C1 and also initial point for U vector. So we will obtain the vector for W1, where W1 equal to 103.3. Okay, relative flow relative flow velocity W1 equal to 103.3 meter per second. And also we can measure by using protractor the value of beta 1, 61.5 degree. For the relative flow angle, okay, so we obtain beta 1 equal to 61.5 degree. So we also can determine by using the trigonometry approach, where for relative flow angle, we know that if we refer to the velocity diagram, we have Wy1 and also Cy1, and tangent beta 1 actually equal to Wy1 divided by Cx1. Manipulate the trigonometry law, we will obtain tangent beta 1 equal to 1.8560. Okay, determine the beta 1 value. The beta 1 value equal to 61.7. For the relative flow velocity W1, we also can determine by using trigonometry approach, where W1 equals Cx1 divided by cos beta 1. Substitute the value that we obtain. So W1 equal to 103.8 meter per second. So because we need to calculate the enthalpy difference, so we need to determine the value of y component for C1, where if you measure by using the velocity diagram, Cy1 value equal to 8.6 meter per second. And also we can determine by using trigonometry approach, where Cy1 equal to 50 sine 10 degree, and the value will be equal to 8.7 meter per second. Okay, next continue for question B. For rotor outlet condition, data and also information given are C2 equal to 80 meter per second, U equal to 100 meter per second. And constant axial velocity condition we already obtained from the previous slide, where Cx1 equal to Cx2 equal to Cx equal to 49 meter per second based on the geometry or graphical approach. So you have to draw this diagram at the rotor outlet to determine CY2 value in equation number 13. So still you need to use your own scale. First draw the vector U, because you already know the magnitude and also the direction. And because we already know the axial velocity value, so we just draw what I call the upper limit and also lower limit line for the axial velocity that the value represent the velocity of 49 meter per second. Okay, so in order to determine the absolute flow angle alpha 2, because we only have the value of C2 without the value of alpha 2, so we cannot draw directly the vector C2. So what we need to do, we need to use the compass. Okay, use compass based on C2 vector, Cx, and also refer to the endpoint of U. Okay, first measure the compass, set the compass so that the distance between 2 points of the compass will represent the value of C2, which is equal to 80 meter per second. And then based on the endpoint of U vector, rotate the compass so that the compass will construct a circle. And the circle must intersect with the upper limit of the axial velocity line. So in order to draw the C2, so connect the intersection point between the circle that construct by the compass and also the upper line of the axial velocity. So we'll have the vector for C2, which is equal to 80 meters per second as shown in the slide. And from the line of C2, we can determine by using the protractor, determine the absolute flow angle value, which is equal to 52 degrees. So alpha 2 equal to 52 degrees. Okay, in terms of relative flow velocity, so we just simply can draw the line for W2 vector by connect the initial point for C2 and also initial point for vector U. So we'll get the line for W2, which is, if you measure, we'll get W2 equal to 61.3 meter per second. And for the relative flow angle, just use the protractor to determine beta 3, which is equal to 37 degree. Okay. And for the y component, if we measure the velocity diagram, the y component for C2, so we will obtain CY2 equal to 63.7 meter per second. Okay, so we also can determine all the data or all the parameter that we measure by using the geometrical or graphical approach. We can also use by using trigonometric approach, where for absolute flow angle, where we know that if we base on the velocity diagram, cos alpha 2 equal to Cx2 divided by C2 equal to 0.615. Calculate the alpha 2 value, so we'll get alpha 2 equal to 52.04 degree. For relative flow velocity, so we know that we have the component for Wy2 in the velocity diagram and also Cy2 in the velocity diagram. Y2 equal to square root Wy2 square plus Cx2 square by implement the what I call the triangle rules. And W2 is equal to 61.5 meter per second. For relative flow angle, cos beta 2 equal to Wx2 divided by W2, where Wx2 is refer the axial velocity for the W2. So the value will be equal to Cx1, Cx2 equal to Cx, which is equal to 49.2 if we base on the value that we obtain from trigonometry approach. And value for cos beta 2 equal to 0.8 calculate the value of beta 2. So beta 2 equal to 36.7, sorry, beta 2 equal to 36.9 degree. Okay, beta 2 equal to 36.9 degree. And we need to know the y component for C2. So cy2 equal to 80 sine alpha 2, 52.04 degree, and the value for cy2 equal to 63.1 meter per second. Okay, in order to determine the enthalpy difference, static enthalpy difference, so substitute cy1 and also cy2 value into equation number 3 into equation 13. So the enthalpy difference for the compressor is equal to H3 minus H1 equal to U multiplied by Cy2 minus Cy1. So substitute all the information that we already obtained. So enthalpy difference H3 minus H1 equal to 5437 joule. Okay, in order to test your understanding for chapter number 5, part number 4, answer the question below. First, the similarity for all the factors that affect the total efficiency of the compressor. So determine the similarity for all the factors that affect the total efficiency of the compressor. Question number 2, the assumption that need to be considered so that the value of H03 minus H01 will be equal to H3 minus H1. Question number 3, two factors that affect the stage pressure rise of the compressor. So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue is also given in the link. So that's all for part number 4, chapter number 5. Assalamualaikum.